Hello, everybody. Welcome back to our seminar. Today, Vishal is going to tell us about minimum spectral radius.
Um, okay. So I will present some results from the two projects which I did on this same problem of minimizing the spectral radius, but for different classes of graphs. So the first one was with my PhD advisor, Sebastian Cioaba and Celso Marques. And the second project which I did is with Dheer Noal Desai. Okay, so I will quickly recall all the terms and the notation that I will use from the graph theory. So starting from what is graph. So in a graph, we have a set of points which we call vertices and set of line connecting some of those points which we call edges. So we have two examples on graphs on four vertices. The graph on the left is a disconnected graph with three edges, and the graph on the right has four vertices and five edges, and it's a connected graph. By connected, I mean, given any two vertices on the graph, there is a way to reach from the one vertex to another just by walking on the edges. So in this talk, I will only focus on simple and connected graphs. By simple, I mean, given any two vertices, there can be at most one edge between them, and the loops are not allowed, where loops are an edge which joins a vertex to itself. So those are not allowed. And another standard term from graph theory is a degree of a vertex. So degree of a vertex V is the number of vertices that vertex V it's directly connected to by an edge in the graph. So for example, for the graph on the left, the degree of vertex A, B, and C is 2. They are connected to two vertices in the graph. Whereas the degree of vertex D is 0. It is not connected to any vertex in the graph. And likewise, for the graph on the right, the degree of vertex 1 and 2 is 3, and the degree of vertex 3 and 4 is 2. They are connected to two vertices in the graph. Okay, so given a graph on n vertices, we can capture this graph by n cross n 0, 1 matrix. It's called the adjacency matrix of the graph, where the rows and the columns of this matrix are indexed by the vertices of the graph, and the entry aij in the matrix is 1 if and only if the corresponding vertices I and j they are connected by an edge in the graph. Else we put 0 in this matrix. So it's a n cross n real symmetric matrix. By spectral theorem, it has n real eigenvalues. So for example, if we have this graph on 6 vertices, where the first 3 rows are indexed by these 3 vertices on the left, and the last 3 rows are indexed by these 3 vertices on the right, we can write down the adjacency matrix and compute all its eigenvalues. So among all the eigenvalues which we are interested in this talk is the largest eigenvalue. It's also called the spectral radius or the index of the graph, which I will denote by a row of G, or sometimes just by row where it's clear which graph I'm talking about. And it's probably the largest eigenvalue is probably the most studied eigenvalue in the literature of spectral graph theory. So Brualdi and Solheid, they pose the following problem that you take set of all 0, 1 matrices and take some subset of it. Now in this subset of matrices, what is the minimum largest eigenvalue and what is the maximum largest eigenvalue of a matrix in this set? And so if we restrict ourselves to only 0, 1 symmetric matrices, they correspond to adjacency matrix of the graph. So in graph theory, people have studied this problem for various classes of graphs. So for example, we are taking a set of all simple connected graphs on fixed n vertices. And the second parameter that we are fixing is as follows. So in case 1, we are fixing the number of edges. In case 2, we are fixing the number of edges and the minimum degree. Or in case 3, diameter, likewise chromatic number, maximum degree, and so on. So the ones in the blue are the ones that I will talk about. So the first class is we are taking all simple connected graphs on n vertices with fixed number of edges e. And the second, we are taking all simple connected graphs on n vertices with fixed dissociation number tau. Okay, so for class 1, the Hong asked the following problem for this problem of minimizing the spectral radius in this class, and it was the problem 3 in his paper from 1993. So let this fancy G and E denote the set of all simple connected graphs on n vertices and E edges. He asked this problem, if G in this set has the minimum spectral radius, then is it true that the difference between its maximum and minimum degree is at most 1? So in other words, is it true that a spectral, we call such graphs spectral minimizers. So in other words, is it true that a spectral minimizer is almost a regular graph? So a very first observation by Courant-Fisher theorem, we know that the spectral radius of a graph is the maximum over all non-zero vectors of length r of this Rayleigh quotient. So if we take this vector to be all one vector, and if the graph has E edges, we get that the spectral radius is bounded above by the average degree of the graph, where equality happens if and only if this all one vector is an eigenvector, and that can only happen when all the vertices have the same degree 2e over n. So the case when this average degree 2e over n is an integer, let's say k, then any k regular graph is a spectral minimizer in this class. And for this case, it's trivially true that the difference between the maximum degree and the minimum degree is less than equals to 1. So what we focused on the remaining cases when n does not divide 2e, that is for the irregular graphs, and we measure the irregularity by this difference between the maximum and minimum degree. And we will show for several cases of E that a spectral minimizer indeed has this difference equals to 1. And in those cases, the only possible degrees a spectral minimizer can have is the floor and ceiling of the average degree. Okay, so what was known for this problem? Since we are working with the connected graphs, the smallest E can be is n minus 1. So we have set up all connected graphs on n vertices with n minus 1 edges. These are the trees. And for trees, Collage and Sinogovich, they conjectured, which was proved by Lovash and Pelikan, that among trees, the path on n vertices is the unique spectral minimizer with spectral radius 2 cos pi over n plus 1. And the star graph is the unique spectral maximizer. That is the graph with the maximum spectral radius in this class with spectral radius square root n minus 1. And by Perrin-Fabini's theorem, we know that if you add an edge to a graph, its spectral radius strictly increases. So if we drop the condition of fixed edges and just consider all simple connected graphs on n vertices, we also get from this result that the path has the smallest spectral radius in this class of graphs. And the next case is when E is n or n plus 1. So when E is n, this case is already handled by the previous observation since n divides 2n. So in this case, a cycle is the spectral minimizer. When E is n plus 1, these are called the bicyclic graphs. And for this, Simic proved that these two graphs in the figure are the only spectral minimizers, where the graph on the left is a cycle of length p and a cycle of length r joined by a path of length q. And the graph on the right is we have two vertices of degree 3 joined by 3 paths of length pqr. And these are the spectral minimizers when these lengths pqr are as equal as possible. Basically, a floor and ceiling of n over 3. Okay. So a natural question here is, what happens when E is n plus 2? These are the tricyclic graphs. Or what happens when E is n plus some constant or k-cyclic graphs? And this problem is still open. So the only known cases for which we knew the answer for minimizing the spectral radius was when E is n minus 1 and E is n plus 1. And for remaining cases, the problem was still open for several decades. So what we focus in our paper is on the other side of this range of E, that is when the number of edges are as close to n choose 2, basically the dense graphs. And so we answered Hong's question for the following cases and we computed the minimum spectral radius for all these cases, and we characterized the graph that attains this minimum spectral radius. So I will try to discuss some of these and try to give an intuition why the following graphs are the spectral minimizers for these cases. Before that, we need another operation. So a join of two graphs. So suppose we have two graphs G1 and G2. They're in their join. We take the graphs as it is, and we add all possible edges between them. So for example, if we take two isolated vertices and cycle C4, their join is this graph on the right. Okay, so so the case one when E is greater than E is in this range from n minus the number of edges in n minus 2 regular graph to the complete graph. And we can write any E in this range by in this fashion n choose 2 minus something, where this something P ranges from 1 to n over 2. And for this range, we showed that when P is strictly less than n over 2, then a spectrum minimizer is a join of complete graph of order n minus 2p and a complete and a cocktail party graph. And when P is equals to n over 2, the spectrum minimizer is the cocktail party graph, where a cocktail party graph is the complement of a perfect matching of a complete graph on even vertices. So it's only defined when the n is even. And the proof idea is really simple. So we observe that for any such E, and so for any graph in this class, has at least n minus 2p vertices of degree n minus 1. So we can rewrite this G as the join of a complete graph with another graph H, where this graph H has 2p vertices and these many edges. And then we can partition the graph into two parts. One part is the complete graph. Second is this graph H. We can write down the quotient matrix and compute its largest eigenvalue. And by eigenvalue interlacing, we get that the spectral radius of G is bounded above by this largest eigenvalue of the quotient matrix, where equality happens if and only if this H is a regular graph. And given the number of vertices and edges, this H is a cocktail party graph on 2p vertices. Okay, so this range is done. Now the second range is this number of edges in the range of the number of edges in an n minus 3 regular graph to n minus 2 regular graph. And for this, when E is n minus 1 choose 2, Jack Cullen asked this following question, that if we take a complement of a 2 regular graph on n minus 2 vertices and 2 isolated vertices and take their join, would that be a minimizer? And we showed that that is correct. In fact, for this case, any spectrum minimizer has the following form. Here I'm using a new notation GNR, where GNR denotes a n minus r regular graph on n vertices. So if we take a n minus 5 regular graph on n minus 2 vertices, it's joined with 2 isolated vertices. That's the minimizer for this case. And for the remaining cases of E in this range, depending n is odd or even, a spectrum minimizer is of the following form. So basically, the idea was we partition the graph into small parts where each part is almost regular and take their join, keeping in mind that the number of edges after taking the join is the number of edges we are working with. So some partitions worked, whereas some did not work. So for example, when E is n minus 1 choose 2 minus 2, we showed that if we take a graph which is n minus 9 regular on n minus 6 vertices and take its join with the spectrum minimizer for the class of graphs on 6 vertices and 8 edges, then that is the spectrum minimizers for this case when E is this. So this inspires this question that can we always do this? For example, if we find out the spectrum minimizers for small values of n and E, take their join, would that be the spectrum minimizers for bigger n? So for some cases it works, and for some cases it doesn't. So yeah. Some other observations is when E is dn over 2 minus 1, where D belongs to this set, we prove that a spectrum minimizer is always a D regular graph minus an edge. So the number of edges are basically number of edges in a D regular graph minus 1. And for this case, a spectrum minimizer is also of this form, a D regular graph minus an edge. Whereas if we take the number of edges equals to the number of edges in a D regular graph plus 1, then it's not necessarily true that a spectrum minimizer is also a deregular graph plus an edge in that graph. And one quick example is the spectrum minimizers for bicyclic case on 7 vertices. So by symmetry result, we know that these two are the only spectrum minimizers, and none of these two can be obtained by adding an edge to a cycle C7. Okay, so the question here is it true in general when E is of this form, dn over 2 minus 1, then a spectrum minimizer is always a deregular graph minus an edge? Or like I said, what are the spectrum minimizers for tricyclic graphs and what are the spectrum minimizers for k-cyclic graphs? And for the remaining cases of E, is it true that a spectrum minimizer has irregularity 1? So there is a paper which appeared last year from Stanich and his research team, and they verified this, that for some special cases of E, and for graph up to order 100, a spectrum minimizer indeed satisfies this inequality. And we believe it should be true for in general for any case of N and E. Okay, then I should stop here and ask if there are any questions for this class 1. Okay, so in part 2, we are fixing the number of vertices. We are taking a set of all simple connected graphs on n vertices and fixed n vertices and fixed dissociation number. So what is a dissociation number? So a set of vertices in a graph that induces a subgraph of maximum degree at most 1. It's called a dissociation set. And the maximum order of a dissociation set is the dissociation number of the graph. So for example, if we take a complete graph, its dissociation number is 2. As soon as we add another vertex, we get a triangle, and the maximum degree will be 2. So it's not a dissociation set anymore. And for path on n vertices, if we delete every third vertex and take the remaining vertices, we get the dissociation number for a path is ceiling of 2n over 3. And for Peterson graph, if we take these 6 red vertices, they give an induced matching, and so it's a dissociation set of 6 vertices, and we can check that we cannot do better than this. So the dissociation number of a Peterson graph is 6. But in general, computing dissociation number is not easy, but we can give some bounds on it. So for example, a dissociation number is always greater than equals to the independence number, because any independence number is a dissociation set, or it's also greater than equals to twice the size of the maximum induced matching in a graph, because any induced matching is also a dissociation set. So there are some bounds known for the dissociation number. We gave one bound using probabilistic methods in terms of the degrees and the maximum degree of the graph. And the proof idea is inspired from a result of Yair, Caro, and Fan Wei. And the idea is we pick a total ordering uniformly at random on the set of edges, and we define the set I of edges where an edge E belongs to the set if and only if we take the set of all edges that are at most distance 2 from this selected edge E. And in this set, this edge E has the smallest ordering. Only then E belongs to the set I. And let xe be the indicator random variable for an edge belongs to this I. And we take the sum, and when we take the summation of all these indicator random variables, we get the cardinality of this set I. And we can compute the expected value of this random variable, which is the expression from the statement. And that means that there exists some total ordering for which the value of this random variable or the cardinality of I is greater than equals to the ceiling of this expression. And the last thing, we note that the subgraph induced by the vertices incident to the edges in the set I has maximum degree 1. They are the maximum induced matching. And therefore, we get this bound on the dissociation number is greater than or equal to twice the number of edges in this set I. So this bound, when we apply it for like complete graph or small cycles, it's tight. But whereas for some easy graphs like path, it is way off. Like it gives us the value of 2n/7, whereas we know that the actual value is 2n/3. So I believe if we change this set I, how we're defining it, we can improve this bound. But our goal was to minimize the spectral radius, so we didn't spend much time on it. Okay, so coming back to the problem of spectral minimizer, but before that, I will quickly talk about the problem of maximizing the spectral radius in the set. So just like for the previous class, we denote the set of all simple connected graphs on n vertices and dissociation number tau by this fancy g and tau. So for the smallest case, when dissociation number is 2, since the complete graph has dissociation number 2, that is the spectral maximizer. When dissociation number is 3, we take a dissociation set on 3 vertices and the remaining n-3 vertices as the second partition. And since we want to maximize the spectral radius, we add all possible edges as possible. So on this set of n-3 vertices, we get a complete graph. And on this set of 3 vertices, we can add a maximum matching, which is just an edge in this case. And we add all possible edges in between them. So the spectral maximizer is the complete graph on n-3 vertices with a maximum matching on this dissociation set on 3 vertices. And the same idea works for any dissociation number k. So depending k is even or odd, we take a dissociation set on k vertices, we add the maximum matching in it, and we take a complete graph on n-k vertices and take their join. That is the spectral maximizer for this class. Okay. For spectral minimizer, the problem is not that easy. So recently, this paper by Huang, Li, and Zhang, they studied this problem for spectral minimizer, and they characterized the spectral minimizers for the following dissociation number. So when dissociation is 2, they showed that a spectral minimizer is a cocktail party graph when n is even, and it's an odd cocktail party graph when n is odd, where the odd cocktail party graph is defined as you take a cocktail party graph of one less order, take its joint with a new vertex. And when dissociation number is ceiling of floor of 2n/3 and n is not 0 mod 3, they showed that a cycle is the spectral minimizer. And for the case when dissociation is ceiling of 2n/3, they showed that the path is the spectral minimizer, which is true because we saw that the path among all simple connected graphs on n vertices, path has the smallest spectral radius, and it has dissociation number 2n/3. So it must be the spectral minimizer for this class. And when dissociation number is n-1, they showed that the following graph is the spectral minimizer, where I have defined this graph on the next slide. So it's the first graph here on the left. It is denoted by SRT, and we obtained this graph by attaching T edges to the center of the star graph of order r+1. So they showed that when dissociation is n-1, by adding n-1/2 edges to the star SR, the graph we get is the spectral minimizer. And when dissociation is n-2, they showed that the spectral minimizer is this graph HN, where the HN is the graph we obtained by adding these many edges to the endpoints of a path of length 3. When n is even, and when n is odd, this graph is obtained from HN-1 by adding just a vertex to one of the endpoints of the path. And these are the spectral minimizers for these cases. And in their paper, they also showed that when dissociation number is greater than 2n/3, then a spectral minimizer is a 3. And the problem was open for other cases of dissociation number. So what we did, our idea was, since we want to minimize the spectral radius, it will be a good idea first to minimize the number of edges. So we change the problem from spectral minimizer to edge minimizers. So fixing dissociation number and fixing number of vertices, we first find out what is the edge minimizer in this class. And if we are minimizing the number of edges in a graph, that means we are maximizing the number of edges in its complement with some restrictions. So we showed the following, that if G is an edge maximizer for a cocktail party graph, that means it has maximum number of edges and it does not contain cocktail party graph. If K is even, or if K is odd, it does not contain odd cocktail party graph. Then if we take its complement, its dissociation number is K minus 1. So, so basically now we change the problem from spectrum minimizers to edge minimizers, and then edge minimizer to edge maximizer for the complement graph, with the condition that it does not contain a cocktail party graph or an odd cocktail party graph. So basically it makes a connection with the Turan type problem where we fix a graph F or a family of graph, and the problem is to find out this Turan number, which is the maximum number of edges in a graph on n vertices that does not contain this fixed graph as a subgraph. And we denote this by small ex, and the graph that attains this number of edges, that is denoted by this capital Ex. Okay, so now our problem changed from spectral minimizer to finding out the Turan number for odd cocktail party graph. So in odd cocktail party graph, let's say we have 2k plus 1 vertices. So its complement will have the dissociation number 2k. So we define this, this set G and 2k. This is a set of graphs we get by, so we are taking a complete multipartite graph on k parts, where with the condition that the number of vertices in each of the parts, they can differ by at most 2. And they can be 2 when both the number of vertices in the parts are even. So it can happen that in one part we have 2 vertices and the another part we have 4. But it cannot happen that in one part we have 3 vertices and in another part we have 5. So only for even the difference is 2. And in each of the parts we are adding maximum matching. So we denote this set of graphs by G and 2k, and we showed that for any order n, an edge maximizer for an odd cocktail party free graph is this graph in this set G and 2k. So now we have the edge maximizer. To get the edge minimizer, we take a complement of it. But the complement of this graph in this set G and 2k, it's not connected. It has k components. And we can connect it by adding k minus 1 edges, but there are many ways to do that. The one way that we focused is this set M and 2k, where we are taking only those graphs where the difference was at most 1. And we are adding this k minus 1 edges in the following way. So in each of the parts, we are taking one non-adjacent pair. So we have k non-adjacent pairs. And we are using only these k non-adjacent pairs to add this k minus 1 edges to get this connected graph. And the reason to do this is we believe that this set contains the spectral minimizer for this class. So first we showed that any graph in this set M and 2k is an edge minimizer in this class with given dissociation number 2k with these many of edges. And the next thing is to show that is it true that any spectral minimizer belongs to this set M and 2k. So we started by a small example. So if we take our dissociation number to be 4, in this case, the k is equals to 2. So we showed that if we take a complement of the set Gn4, and so we have 2 parts, and we connect it by an edge in any manner, those are the only graphs which are the spectral, which are the edge minimizers for this class. And among those graphs, only those graphs which belongs to M and 4, they are the spectral minimizers for this class. Precisely when n is 0, 1, or n is this mod 4, these are the spectral minimizers for this class. but the general question, is it always true that a spectral minimizer is always the edge minimizer and always belongs to this this set Mn2k is what we are still working on. And for the edge minimizers, when dissociation is an odd number, so in this case we are forbidding the cocktail party graph. So uh, the following results by Erdős and Simonovich, in which they are forbidding a complete multiparted graph with d plus 1 parts, where each part has a number of vertices Ri. They showed that when Ri is the first part has R1 vertices and it is 1, 2, or 3, and it's an increasing, the number of vertices is an increasing order, then an edge extremal graph for this complete multiparted graph free is the following graph, where the first part N1 is an edge extremal graph for K2 R1 R2. So in our case, we are taking R1 to be 2 for cocktail party graph. So if we take the first part, which is edge extremal for C4, and for the other parts, they are edge extremal for P3, and take their join, that will be the edge extremal graph for a cocktail party free graph. But we don't know what this graph looks like precisely. So we showed that as soon as we know what this graph is, we take its complement, make it connected, and that will be the edge minimizer for odd dissociation number. And we generalize their result. So in their result, R1 has the condition that it can be 1, 2, and 3. We notice that we can further generalize this condition on R1, that if when R1 satisfies this inequality, then the edge extremal graph for the same graph has the same form. And some questions to think about for this is it true in general that a spectral minimizer is also an edge minimizer for this case? For example, when dissociation is 2, we can show that the cocktail party graph or the odd cocktail party graph, they were the spectral minimizers, and we can show they are also the edge minimizers. And from the result of Huang, Li, and Zhang, since for dissociation greater than 2n/3, the spectral minimizer is a tree, so clearly it is also an edge minimizer for this case. And what are the spectral minimizers for the remaining cases of dissociation now? Okay, I stop here.
Thank you very much for your talk.